Okay, hi everybody. A very good evening. Hope everybody's doing great. Right. So we are supposed to do aldehydes, ketones, carboxylic acid test today, but I was not available. So we'll do it today, and chemical kinetics will be doing it on Saturday. That is tomorrow. I hope you got the information that we'll be having class tomorrow at 6 o'clock, right? So we'll be doing aldehydes, ketones, carboxylic acid now, and tomorrow we'll be doing chemical kinetics, right? Fine. So with that being said, we share my screen, host to disable. Yeah, they will do it. Okay, I am the host. Okay, is everybody able to see my screen clearly? Guys, is my screen clear? Are you able to see the slides?
Yes.
Okay, good. Right. So aldehydes, ketones, carboxylic acid test. So hope you remember how are you going to go about it. We'll be solving some questions, and wherever required, we'll be I'll be seeing the concepts also.
Sir,
Okay.
can you present the screen? Like, can you full screen?
Full screen? No, but the problem is full screen. If I do whatever I write, whenever I go back, that is not coming here, and you'll not be able to see what I'm writing. I mean, in the sense that you'll be able to see what I'm writing, but in the sense that when I send the PPT to you, you're not able to see the writings, annotated part you're not able to see.
Oh, okay.
But you're able to see this, right? You're able to see the screen properly.
Yes, sir. No problem. Yeah.
Okay. And if at all you tell me you're not able to see, I'll zoom it and show it to you. Okay. Right. Fine. So first question, the IUPAC name of this particular compound. Just give me 1 second. I done. Okay, sorry. Okay, so they're asking what is the IUPAC name of this compound, right? So if I have to just draw it and show it to you again.
Sir, option C.
Yeah, cyclopentan carvaldehyde is the answer. Yes, absolutely. But generally what we do is, someone in the chat. Yeah, option C is the answer. Absolutely. Right. So whenever we go for this structure, right? So we have CHO here. So people will generally go for cyclopentanal. Like that's what people generally say. But if I write cyclopentanal, right? Now what I understanding is cyclopent is accounting for this particular 5 carbon atoms. But if you write cyclopentanal, you're seeing that only 5 carbon atoms are accounted for, right? So in those cases, you have to go for carbaldehyde, right? So the answer would be cyclopentan. Carbaldehyde would be the answer. The same will happen if I go for this one, say CHO, CH, CHO, CHO. Like if you have these kind of structures, you see that any one of the aldehydes you're not able to include in the main chain, right? So obviously you will not take into anything. So you will write this particular one as the main chain. So you will write methane, right? 1, 1, 1, you'll write, and then you'll write tricarbaldehyde. Okay, I'll just do it in a fresh page. Just a second. Right. Say for example, if I have CHO, CHO, and another CHO. Now, what you understand is you cannot include all of them in the main chain, so you don't include any of them. So you will include this only in the main chain. So you will write methane 1, 1, 1. There's only one carbon atom, and that is only having these 3 CHOs. So you will write carbaldehyde.
Sir.
Yeah.
Sir, 1,1,1 trial.
No, tricarbaldehyde. Absolutely. Absolutely. Yes. It should be tricarbaldehyde. Yes. Okay. Right. So this you will.
Can we use AL instead of carbaldehyde?
No, you cannot use AL, because if you use AL, what will you choose? You will choose this one or this one or this one. What will you not choose in the main chain? Everything is CHO, right?
Okay.
So you cannot use it this way. So everything has to be considered similarly. So you'll write methane 1,1,1 tricarbaldehyde only. Okay. Right. Moving on. When a mixture of calcium benzoate and calcium acetate is dry distilled, the resulting compound is okay. Now this is the shortcut I'll tell you. Now calcium benzoate is going to look like this: C6H5, C double bond O, C. Okay, C double bond O is there, and then this is going to have Ca2 plus. Okay, and I'm going to have calcium acetate also. That is Cu2 plus is there. And I'm going to have calcium acetate also. Calcium acetate is CH3CO minus, right? Okay, this is what we have. So we have this anion, and this cation, right? And whenever I go for dry distillation, remember that we need to remove CaCO3. Okay, CaCO3 has to be removed. So Ca is here. So one carbon atom, there are two oxygen atoms coming, and one more, this thing is coming. Now you see Ca, C, 1, 2, 3. CaCO3 is getting removed. Now all you have to understand is you have to merge this with this. So how do we write C6H5, C double bond O, CH3? This would have been the product of the reaction. Okay, very, very simple. Whenever they go for dry distillation, calcium benzoate, something is given, all you have to do is remove your CaCO3 and merge the compound. Right? So what is the name of this compound? Acetophenone? Is it not? Right? Acetophenone yes, is what is going to be the answer for this question. A. Right? Next. The formation of cyanohydrin from acetone is which type of reaction? What is cyanohydrin? Say I have, for example, any C double bond is there, right? And if I put first Cn minus, now you understand that this carbon is going to have a del positive and this oxygen is going to have a del negative, right? So all of these carbonyl compounds will undergo a specific reaction called as nucleophilic addition reactions, right? Now you might have seen difference between electrophilic addition, nucleophilic addition. Both of them are going to have electrophile as well as nucleophile, right? But it is all about which attacks first. If it is nucleophile attacking first, it is nucleophilic addition. If it is electrophile attacking first, it is going to be electrophilic addition. And in which kind of compounds will have electrophilic addition?
Pi bond, double bond.
Yeah, that is when you have C double bond Cs. Okay, when you have C double bond C, it is electrophilic addition. When you have C double bond O, they'll always undergo nucleophilic addition. Now, how will you show the mechanism? This Cn minus is going to attack this particular carbon atom, and in that process, this bond breaks. So you will write C O minus. There are two more bonds, and you have Cn. And obviously, you will actually adding HCl. That's what you'll have. So you'll have H plus that will be taken up by the OH to mean O minus to form OH. So this is what is called as your cyanohydrin. Right? Hydrin is basically OH, right? And your cyano is Cn. So both the compounds are there, both the functional groups are there in the same carbon atom. So these are called as cyanohydrin. Obviously, the example for nucleophilic addition reaction. Okay, fine. Next, moving on. Which of the following reactions, which of the following reagents, carbonyl compound shows addition cum elimination? Okay. Addition cum elimination. PCl5, Brady's reagent, HCN is nucleophilic addition. What is Brady's reagent? This and all I don't think is there in the syllabus also for you, these reactions. Don't worry about this, Kana. This is not in the syllabus. It's not even in the syllabus for you, right? They have taken from some JEE means or something, right? If you're interested, maybe I'll just tell you what is this Brady's reagent. Just give me a second. I think the answer is going to be Brady's reagent only. Two, 4 dinitrophenylhydrazine, but this will also undergo only nucleophilic addition. Okay, don't worry about this. Okay, right, we'll move on to the next question. Next, a mixture of benzaldehyde and formaldehyde on heating with aqueous NaOH is going to give you what? What reaction is this, people? What reaction is this? I have, sorry?
Is it aldol?
Okay, now how do you decide both your aldol and
Sorry,
another
sir.
one?
No, Canisararu. It doesn't have aldol.
Right. So both aldol and canisaro, both the cases, you will use aqueous NaOH only. Right. Both the reagents used are in aldol condensation as well as in canisaro, it is going to be aqueous NaOH only. But how do you decide
Here,
whether it is
alpha hydrogen is not there.
Exactly. Right. For aldol condensation, we need to have at least one alpha hydrogen. Right. Whereas canisaro, we should not have any alpha hydrogen present. Okay. Right. So if I have this one, CHO, this is benzaldehyde, and if you have HCHO, that is your formaldehyde, on heating with NaOH, this is an example. This is canisaro, obviously, and in this canisaro reaction, you see that disproportionation reaction is going to happen. That means one of them is going to get oxidized, one of them is going to get reduced. Right. Now tell me which will get oxidized, which will get reduced. When I say oxidized, whatever is getting oxidized, aldehyde getting oxidized is going to give you what? Acid, right? And aldehyde getting reduced is going to give me alcohols, right? So which is going to give me alcohol, which is going to give me acid? And how do you decide that?
Sir, formaldehyde forms formic acid.
Okay. Is there any logic behind it?
The smaller group prefers oxygen.
Okay, you don't know the mechanism of this, right? If you know the mechanism of this, you'll be able to easily understand this, right? Maybe not today, right? Whenever we get some time, I'll show you how this mechanism works. Okay. Now at that time, you will see that this hits all, or maybe if you can just show you a little shortly, all that you have to understand is, I have HCHO, right? I have H and H here. Now basically OH minus from the NaOH is going to come. Okay. Now this OH minus comes and attacks here, and this bond breaks. And eventually it is going to come back, right? Okay, let me actually, what is there? Let me show you the mechanism. Right. So we have, what is this? HCHO. And we have OH minus coming. And this OH minus is going to attack this, and this bond breaks. So what is going to happen? We are going to have O minus, H, and I have a OH, right? Now, when this bond comes back, makes a double bond O, I am going to take out a hydride, okay? So that is going to give me H, C double bond O, OH. Now you form the formic acid, right? And what is remaining is H minus, right? Now this H minus is going to attack your benzaldehyde. Again, this H minus will attack here, and this bond breaks, right? And obviously what is going to happen after that? We are going to have this, we have C, O minus, we have a H, and we have another H. Now, obviously this O minus will take up a H plus to form OH. Now, what do you see? This is going to form alcohol, and this is going to form formic acid. But why is it that this OH minus, I was attacking to this one, right? If this OH minus were attacking this one, that is your benzaldehyde, that would have formed your, acid, and the H minus would have attacked your this one, and that would have formed the alcohol. Why is it this like this only I'm taking? Any idea?
Sir, SN2 reaction, sir.
SN2, why? Where is substitution happening here? This is an example for nucleophilic addition.
Sorry,
right?
yes, sir, yes, sir. Sorry, sir.
Right? This is an example for a nucleophile attacking this particular carbonyl carbon. This is an example for nucleophilic addition, right? So if I give you 2-3 compounds and ask you to decide which will undergo easier nucleophilic addition, how will you approach these problems?
Sir, in benzene, it is sp2 hybridized carbon.
And here also it's sp2 hybridized only, and say benzaldehyde also. Anything which is having one pi bond will be sp2 hybridized. Okay.
Sir, in
Right.
benzene resonance occurs, sir.
So, okay, guys, this is how we will look into it. Right. So now I am going to have this C double bond O, which is going to have a del plus, right? And then comes your nucleophile. Okay. Now, can I say this reaction will be more and more faster if this charge on the carbonyl carbon is going to be higher and higher? Is it not? Because that is going to have a great attraction towards this nucleophile. Is it not? Right? So now, if I want to compare, say, HCHO with CH3CHO, right? And say if I compare it with CH3, C double bond O, CH3, right? Now all of, say, this is one del 1 plus, this is del 2 plus, and this is del 3 plus. Now tell me which del is greater? Which del is the greatest?
First one,
Okay, which is the least?
third one.
Why?
Sir, CH3, it's an electron donating group.
Absolutely.
Reduces
Right. Now we can understand that all your alkyl groups are electron donating in nature. Is it not? Right. So that's the reason why this electron donating means negative charge is coming towards. So obviously this del 3 plus would have been the least value because electron donating groups are present, and del 1 plus will be the greatest. Okay. Right. So what you can say is the reactivity towards your reactivity towards your nucleophilic addition reaction is directly proportional to the electrophilicity of the carbon. When I say electrophilicity, what is electrophilicity? The positive charge on the carbon. Okay, that is the first criteria to look for. Right. Now, what if I have CH3, C double bond O, CH3 with both are ketones. Now tell me, which do you think will be more reactive? The first one or the second one?
First one.
Why?
Sir, here it is attached to 3 alkyl groups. Here only 2.
How 3 alkyl? How it is 3 alkyl groups? There is
Second
1,
one, sir.
2. Here it is 1, 2. Benzene ring is the other alkyl group, right?
Second one,
Second one is more reactive. See, now if at all, generally aldehydes are going to be more reactive. We can conclude that. When I compare an aldehyde and a ketone, definitely aldehyde is going to be more reactive. Okay, right. And when I compare 2 ketones, then how do you do it? Is with the help of steric hindrance. Now understand that the nucleophile is going to attack both of them. Right? The nucleophile is going to attack both of them. Now you understand that this is going to be a very bulky group. It's not so big it is. Right? So this will hinder this nucleophile approach here. Right? So we can say that the first one is going to be more reactive because it is less sterically hindered.
Sir?
Yeah.
sir, but in the second case, due to the pi bond, it pulls the electron towards the benzene.
No.
So it creates
If you can draw the resonance structure for benzaldehyde, you will see that this double bond which is here will go like this, not the other way around. Okay, this double bond will go and this bond breaks like this. This is how you show the resonance structures.
Okay.
And only if you show the resonance structure, you can show that these are metadirectic groups. We know as aldehydes and ketones are going to be metadirectic groups, right?
Yes, sir, yes, sir.
Obviously, because this is going to act as electron withdrawing group for benzene, not the other way around.
Yes, sir. Okay.
Okay,
Okay.
right? So obviously 2 things you will look for, people. One is the amount of charge, right? And second thing is steric hindrance, right? Steric hindrance means crowdedness. Okay, so less and less steric hindrance it has, more and more reactivity it is, and more charge it has, more and more reactivity it is. Okay, so when I come back to this one, now you see that definitely this is going to be having more electrophilic nature because this is an aldehyde, this is a ketone. Okay, or maybe this is both are aldehydes, but you understand that again I'm going to have a very bulky group here that is going to be less reactive towards nucleophilic addition. So that is the reason why your aldehyde, the smaller ones forms your aldehyde acids and your bigger ones will form the alcohols. Anybody has any questions? Okay, fine. So what will be the answer for this question? Obviously, I'm going to form what is that? HCOO minus Na plus. Now, why is it not HCOOH? Why is it going to be HCOO minus Na plus, people? We are forming HCOOH only, right? But the actual product
Because
is
reagent has NaOH, so when it dissociates, Na plus ions will be there.
Is that how you explain it?
Na is more electropositive than.
No. Is that how you explain it? It's very simple, right? HCOH is an acid. right? Let me go here. Right, if I can just write the reaction here, HCOOH is an acid and NaOH is a base. Acid-base reaction is going to happen. What will happen? So this H plus will be replaced by Na plus. So you are going to form HCOO minus Na plus, and other product is going to be water. Acid-base reaction, normal acid-base reaction would happen. Is it not? So that is the reason why we are forming HCOO minus Na plus. Right? Okay. Moving on. So what should be the answer? So obviously you're going to form sodium formate. Where is it? Formic acid, and salt of formic acid is what is called as sodium formate, and you are going to form benzyl alcohol. So A is the answer to this question. Anybody has any questions?
Yes, so smaller one will undergoes
Oxidation.
Okay, so it gets converted to
Acid. And that acid will react with NaOH to form the salt of the acid.
yes, sir. Okay.
Okay. Right. Moving on. Right. Which of the following organic compounds answers both iodoform test and Fehling test? First, iodoform test, what should be present?
CH3C double.
Exactly. So this stuff, this particular side group must be present. CH3C double bond O must be present. Okay. And Fehling's test is given by what?
Aldehydes.
Aldehydes only. Okay. So obviously you can neglect all of them, right? And you can just write CH3. Now you see that ethanol is going to have CH3, C double bond O and a H. Now you see that this CH3, C double bond O group is there, right? So definitely that is going to give iodoform test, and as well as it is going to give Fehling's test. Very simple. Okay. Moving on. Next, the chemical that undergoes self-oxidation and self-reduction in the same reaction. Now they're asking about what? They're asking about, again, a Cannizzaro reaction. So for Cannizzaro reaction, I should not have any alpha hydrogen, right? And first of all, it should be an aldehyde or a ketone. Now acetone definitely has alpha hydrogen, right? CH3, C double bond O, CH3. This is your alpha carbon. This is your alpha carbon. There is definitely 3 hydrogens, 6 alpha hydrogens are present. So this is not going to be the case, right? Obviously, what is going to be the answer? Formaldehyde. H, C double bond O and a H, which doesn't have any alpha. First of all, it doesn't have any alpha carbon also. So definitely it doesn't have any alpha hydrogen. So it will give, if it undergoes self-oxidation, self-reduction, it is going to give me HCOO minus Na plus. And what is the other product? Self-reduction.
Methanol.
Exactly. CH3OH will be formed. Okay. Right. So maybe if at all I give you the reaction, HCHO on reaction with NaOH is going to give me HCOO minus Na plus CH3OH. Okay, right. Next, the IUPAC name of this compound is, right, now I just write the structure bigger for you. We have a double bond O, OH, and we have a double bond here. Okay, now what group is this?
Acid.
What group is this? Acid. See the COOH, C double bond OH is acid, right? So definitely you see that this is the first carbon atom we'll mention because that is the maximum priority. 1, 2, 3, 4. So it should be butyric acid. Right? We'll see what is going to come in. Right? Now what you have to understand is 1, 2, 3. The third carbon atom we have a double bond also. So you should write it as but3N-oic acid. Right? So obviously the first one is going to be the answer. Right? Double bond or COOH is going to have more priority. COOH is going to have more priority. So that COOH's carbon is what is going to be numbered 1 and not the other way around. Okay, moving on. Which is most acidic? Now, how do you go for this? Guys, this kind of questions are very, 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 very common. All that you have to understand is the acidic strength is directly proportional to the stability of the conjugate base. Okay, the acidic strength is directly proportional to the stability of the conjugate base. What is a conjugate base? Guys, in general, in chemistry, what do you mean by conjugate base?
So acid after losing hydrogen.
Absolutely. Right. So if at all I have an acid HCl like this, and after removing H plus, whatever is remaining, Cl minus, this Cl minus is what is called as your conjugate base. Right? So from an acid, after removing H plus, whatever is going to be remaining is what is called as your conjugate base. Right? So if at all you want to talk about the acidic strength, first you remove the H plus, make the conjugate base and check for its stability. Right? Okay. Now what and all is given to us? Okay. So fine. We'll just make another page and do it. Right? So we have been given CCl3COOH. Right? Then we have given, then we have been given CHCl2COOH. Then we have been given CH2ClCOOH. Right? And then we have been given CH3COOH. Okay. So we'll just remove H plus from all of them. We'll make a minus. We'll remove H plus from all of them. We'll make a minus, minus, minus. Now these are the conjugate bases. Right? Now how do you check for stability, people? Your stability is inversely proportional to the charge. That means more and more neutral it is, more and more stability it has. That is understood. Is it not? Lesser charge, more stability. Right? So now you understand that CCl3 is there. Now all the Cls are going to be very, very, very high electron to electron with the drawing groups they are. Is it not? They're very highly electronegative. Right? So they will be able to decrease this negative charge to a 3-time decrease will happen because there are 3 chlorine atoms. And in this case, there are going to be only 2 chlorine atoms, so double time decrease will happen. Here only 1 chlorine atom is a one-time increase. In this case, nothing is there to decrease it. Right? So can I say this one is going to be the most stable conjugate base? And obviously that particular acid will be the strongest acid. This is, again, I'll repeat all the points. The acidic strength is directly proportional to the stability of the conjugate base. What is conjugate base? After removing H plus, whatever species is remaining is what is called as conjugate base. Now, how do you decide the stability of the conjugate base? Less and less charge it has, more and more stability it has. Right? So obviously in this case, we have 3 electron withdrawing groups, which is going to decrease the negative charge. And that is the reason why that is going to be the strongest acid. If I have to name, if not able to give rank for them, this will be the strongest, this will be the second strongest, this will be the third strongest, and this will be the least acidic of them all. Okay. Anyways, so the answer to this question is obviously going to be what? CCl3COOH. Okay. Right. Next, moving on. Which of the following compound cannot reduce Tollens reagent? Which cannot remove? What is the answer? I think it's a printing mistake. This is HCHO. Okay, obviously ketones cannot do it, but a bad acid can do it. What is this? HCOH is given, that can do. Okay, that's an exception. Okay, now in HCOOH, if you write the structure, this is what is the structure, right? HCOOH. Now all I have to understand is I need to have the CHO group, that is C double bond O H is there. Right? So that is the reason the only carboxylic acid which will give Tollens test is HCOOH. No other acid can give. Because another acid, this is going to be carbon atom. CH3COOH or C2H5COOH, whatever it is. Okay, so this is again a very good exception. HCOOH, that is acidic, formic acid, is the only acid which will give us Tollens test. No other acid will give. Right? So obviously the answer to this question would be
sir.
Yeah, tell me.
Sir, then in option C also CHO is there now.
Yes, it will give. Obviously, they're asking what will not give.
Oh, okay, understood.
Right? Okay. I mean, all aldehydes will give, right? And only acid which will give is HCOOH. Actually, one more compound gives Tollens test. That is your CH triple bond CH. Weirdly, this also gives Tollens test. Okay, then alkyne. This is again only one alkyne will give. That is your CH triple bond CH will also give Tollens test. But again, it's too much for your CBSE NCRT level. But don't worry about it. Okay. Next, moving on. Formic acid can be distinguished from acetic acid by reaction with what? Formic acid can be distinguished with from basically talking about formic acid is HCOOH, and we have to distinguish with reaction with CH3COOH. Tolerance is not given, right? What is given, you check.
Sir, DNP.
2,4 DNP. Yeah, similarly, basically it is again going to have this CHO group, right? So definitely whatever kind of aldehydes will give, whatever they test the aldehydes will give, your HCOOH also will give, right? So NaHCO3, both of them will react because both are acids. Acidified KMNO4, nothing will happen in both of them. And sodium metal, again, both of them will react. This H plus will be replaced with Na plus, right? The only correct option would be C, 2,4 dinitrophenyl hydrazine, that is 2,4 DNP test. Again, for the same reason why this gives tolerance test, the same reason it is going to give my 2,4 DNP test also. Can ketones give 2,4 DNP?
No, sir.
No, I don't think the answer is 2,4 dinitrophenyl hydrazine. I think it's going to be acidified KMNO4. Yeah, ketones cannot, ketones will give, okay? Anything which has C double bond O except for acids, right, will give 2,4 DNP test. Okay, ketones will give, aldehydes will give, but I don't think acids will give. The answer should be, I think, acidified KMNO4. This is not the answer. Okay, the answer is B. Okay, now how am I saying this? Is because this HCOOH can easily lose carbon dioxide and it will form water also. This will happen because of oxidation. Now, how do I prove that this is oxidation? Let me prove it to you. Basically, KMNO4 is going to be an oxidizing agent. Is it not? KMNO4 is going to be an oxidizing agent, which will easily oxidize your HCOOH to CO2. CH3COOH, nothing will happen. Okay. Now, how do I prove that this is oxidation to you? Let me prove that. Right. So now you see H, C double bond O, OH. Right. I don't know. You have studied this in redox reactions in 11th class. If I have to calculate the oxidation state of this, there is for this oxygen is going to give me -2. So this is going to be +2. This oxygen is going to give me -2, but minus +1 for this, +1 for this. And this hydrogen is going to have a -1, and that is going to give me a, sorry, this hydrogen is going to be a +1. So this is going to give me a -1. So all you have to understand is for each covalent bond, -1 goes to a more electronegative atom and +1 goes to less electronegative atom. Obviously, you have oxygen to be there, -2 it will get, and there are going to be a double bond. So for each bond, +1 will come for carbon because carbon is less electronegative. And same goes here. There is only a single bond, oxygen is there, oxygen will get -2, and hydrogen will get a +1, and this carbon also will get a +1. And for CH bond, carbon is more electronegative, that will get a -1. So now if you have to calculate the oxygen state here, +2 +1 -1 will give you +2. Okay. Now in CO2, what is the oxygen state of carbon? You can easily see that it is going to be +4. That you can write X - 4 is equal to 0. You'll get +4. Now you see +2 to +4 is oxidation, right? And HCOH can easily do this, whereas CH3COH is not going to do this. Okay. And how do we distinguish it? Okay, we see that, CO2 is coming out, H2O is coming out, CH3COH is not able to do that. But how will I identify? How will I know whether the reaction is happening or not? Or how do you, I don't know, if the one way you can say is by seeing that CO2 is getting evolved and you will be able to put it in lime water and that lime water turns milky, right? You might have seen this reaction in 10th class, lime water turning milky.
Sir, or candle, sir, if you take a candle.
A candle will get extinguished. There is another way of looking at it. But the most easiest way is that if you look at KMNO4, KMNO4 is going to be purple in color, right? And in this oxidation process, this KMNO4 is going to get reduced to Mn2+. Mn2+ is going to be colorless. Okay. Now that is how you identify. The purple color of the solution at the end of the reaction, it is going to become colorless. That means you see that this is going to get oxidized. Okay, this is how we can say. And various other methods are there because CO2 is getting evolved. Right. So the answer to this question is acidified potassium dichromate, that is KMNO4.
Sir, why it is not 2,4 dinitrophenyl hydrazine?
Because the 2,4 dinitrophenyl can only be aldehydes and ketones. Your acids cannot give. Okay.
Yes, sir, but we can distinguish like formic acid produces positive test for 2,4 dinitrophenyl and acetic acid.
No, Kanna, it won't react. That's what I'm telling. HCOOH will not react with 2,4 dinitrophenyl hydrazine. Only if it reacts, you can talk about some distinguishing.
Sir, but
right?
aldehyde is present in HCOH, right?
Actually, the previous one, I just wanted to explain you, that's why it is happening. But the main reason why it is able to give me tolerance test, this HCHO, is not because it is having a CHO group, right? Why it is happening? Because your tolerance reagent is also going to be a mild oxidizing agent. Okay, a tolerance reagent also is going to be a mild oxidizing agent. So in this process, when I go for tolerance, if I add tolerance to this, is going to give me CO2. And in that process, your silver is going to get precipitated. Okay, so HCOH can easily undergo decarboxylation, we call it. I don't know whether you've seen the reaction, decarboxylation. That means what? I'll be able to easily remove CO2 from HCOH. Okay, that is the reason why it is giving me tolerance test. But yeah, for your understanding, I said it is having a CHO, that is why it is giving. But the overall idea is the same idea what we saw in your KMNO4. Right? Tolerance reagent being a strong, little medium oxidizing agent, it is going to oxidize your HCOH to CO2. That is why it happens.
Yes.
Okay, right? Okay, next. Okay, next. Although aldehydes are easily oxidizable, the corresponding carboxylic to the corresponding carboxylic acids, yet propanol can conveniently be prepared by the oxidation of propanol by acidified potassium dichromate. Acidified potassium dichromate, basically, if I have any RCH2OH, that is, if I have any primary alcohol, and if I have a strong oxidizing agent, right, now that is going to give me RCOOH, right? Potassium dichromate is actually an oxidizing agent, but why propanol? It is going to stop with propanol. That means if at all, basically, if I want to have RCH2OH forming RCHO, we need to use a weak oxidizing agent. Only then it is possible, generally speaking. Okay. But in this case, potassium dichromate is there. It is able to oxidize. It is able to stop at your this thing itself. That is your propanol itself. It is not going to go to propanoic acid. Why? What is so special about propanol? Or that is, it is going to form CH3, CH2, CHO, and potassium dichromate. Why is it like this? Okay, we'll check the question on Google.
Sir?
Hmm.
Sir, in the question, the first line speaks about aldehydes easily oxidizable to carboxylic acid. But the second sentence speaks about propanol can be easily prepared from propanol.
Propanol can be prepared from propanol. Yeah, that is also true. But this, whatever I explained to you, is also true. Primary alcohol to acid. Just a second. Alcohols can be oxidized. Not able to find the answer. Okay, remind me. I'll do my research and let you know why is it like this. Okay, tomorrow's class, please remind me. Okay. Right, we'll move on to the next question. We'll not waste time. Next one. Explain why dialkyl cadmium is considered superior to the Grignard reagent for the preparation of ketone from acid chloride. So what reaction are we talking about? We are talking about RCOCl, right? Reacting with RMgX. Now what is going to happen? This R minus is going to come and attack here, and this Cl minus leaves, right? So you are going to have RC double bond OR. This is how the reaction happens if you use Grignard reagent. The same thing will happen if I use R2CD, that is dialkyl cadmium. Again, R minus is going to come. That the same reaction is going to happen, right? They're asking why is it that R2CD is superior when compared to your what is that RMgX. Now that is very simple. It's because this now you see that more and more ionic it is, right? More and more ionic that particular alkylating agent. When I say alkylating agent, which is going to give me the alkyl group. Okay, which the more and more negative charge, the more and more ionic this particular that particular R minus or that particular compound is, more and more is going to be the reactivity. Then obviously when I can compare it with magnesium with cadmium, cadmium is going to be more metallic. Or that is one way of speaking about it. Second way of speaking about it is there's only one R minus coming, but here I can have two R minus coming, so more probability of adding this R minus. Okay, either way you.
Sir, twice the amount of product will be formed, right?
Exactly. Twice the amount of product can be formed. Absolutely. Because there are two alkyl groups present in R2CD. Right? Like that way you can speak. Right? Okay, just give me 1 second. I'll be back. Right. So next question. Okay. Although C double bond C and C double bond O have a double bond, they exhibit different type of addition reactions. We have seen this, right? C double bond C undergoes electrophilic addition, whereas C double bond O undergoes nucleophilic addition. Why is it like this? It's very simple. When I take this C double bond C, all that you understand is this pi cloud is there. It is going to have high negative charge. Right? Obviously, if an electrophile comes, that is can easily get attracted towards this negatively charged pi electron cloud. Whereas in C double bond O, what do you see? There is a del plus on this carbon. Because of that, the nucleophile can only attack. Right? This is how you show it. Okay, you have to say that in C double bond C, the pi electron cloud is having a very high negative charge, very high electron density, and that is why electrophilic addition reaction happens. Whereas in carbonyl compound C double bond O, the carbon is having a positive charge, a partial positive charge, and that's the reason why it is undergoing nucleophilic addition. Very simple, right?
Sir,
Moving on. Yeah, tell me.
Sir, for the before question, that the Grignard reagent question, can we write the reason as a Grignard reagent should be stored in a dry place and the cadmium doesn't need something like that?
No, Kana, this dialkyl cadmium also is like that only. You have to store it in dry place only.
Okay, sir.
Okay, right? Fine. Okay, why is it like this, people? Why is it that the Grignard reagent or these dialkyl cadmium has to be stored under anhydrous conditions? Why is it like that?
It forms as respective alkyl.
Exactly. Right? Even trace amount of H plus you have, this R minus will be able to react with H plus to form RH. That is alkane, hydrocarbon. Okay. Anyways, next. Right. Why is aldehyde more reactive than ketones? We have seen 1,000 times. Two reasons. What? Because there is going to be more partial positives on the carbon atom on aldehydes. And what is the second reason?
Steric.
Steric hindrance. Aldehydes are less sterically hindered when compared to ketones. Two reasons you will write. Okay. Moving on. Benzaldehyde reduces tolerance test, but not Felling's test or the Benedict solution. Why? I don't know why are they asking these kind of questions to you. Anyways, no issues. Right. Benzaldehyde reduces tolerance reagent. Obviously, the aldehyde, it will be able to reduce your tolerance reagent. But being an aldehyde, it is not going to give me Felling's or Benedict's. Now, why is it like that? Now, it is because obviously, or basically, they have to get oxidized, right? This tolerance reagent, Felling's reagent, all of these things are going to be oxidizing agents. That's what I told you. For example, if you have any aldehyde, and if you go for tolerance or Felling's, okay, or Felling's, all you have to understand is I am going to form oxidized product. RCOO minus is going to get formed. Your aldehyde is going to get oxidized to RCOO minus. And in that process, some change will happen for the metal. So Ag will get precipitated, or Cu2O will be getting formed, and because of the color change will happen in case of Felling's. Okay. But why is it that your Felling's or Benedict is not able to do it? Because these are weaker oxidizing agents when compared to tolerance. They are weaker oxidizing agents when compared to your tolerance, and that's why your benzaldehyde being a very strong this thing, I'm going to have a C double bond character also, right? Is it not? I'm going to have this double bond CO minus is going to be there, and this H is going to be there, and partial double bond character is there, and that's the reason why it is. I need a very strong oxidizing agent. That means tolerance reagent is strong enough to do this, but your Felling's or Benedict's is not strong enough oxidizing agent to conduct this particular reaction. Okay, this is how you must write the answer. Okay, right. Tolerance reagent is a little more stronger reducing agent compared to Felling's or Benedict's, and that's the reason why it is able to give, whereas your Benedict's or Felling's is not able to oxidize your benzaldehyde. Okay, right. Moving on. Okay, dipole moment of aldehydes and ketones are higher than those of alcohols. Right. Now, how do you calculate dipole moments, people?
Charge into distance of separation.
Right. So basically, you have to see C double bond is there, and we have this COH bond. Right. Now, this is going to have a del plus. This is going to have a del minus. This is going to have a del plus. This is going to have a del minus. Right. Both of them are having some kind of partial positive, partial negative charges. And you see that the dipole moment mu is equal to the charge del into D. That is the distance of separation. Right. The aldehydes, and they're telling that aldehydes and ketones are having more this thing when compared to your alcohols. Now it's very simple. Obviously, you have to speak only in terms of the amount of del plus and del minus. Right. This del plus and del minus, wherever it is going to be higher, and that is where it is going to be highest. The dipole moment is also going to be highest. Right. So you see that here hydrogen atom is there. Right. Now this hydrogen atom is also going to have some del plus. Is it not? This OH bond, this is also going to be polar. So because of this del plus, you understand that this del plus is going to get reduced, right? The carbon's del plus is going to get reduced because of some del plus getting developed on the hydrogen. Whereas here, there's nothing like that. Is it not? There is no hydrogen atom here. This del minus is going to be solely for this, and this del plus is going to be solely for this, right? So how you should write it is, the partial positive charge on the carbon atom and the partial negative on the oxygen atom is going to be higher in case of aldehydes and ketones, and it is going to be lesser in terms of alcohol because your OH bond is also going to be polar. When I say polar means they'll be able to give me del plus and del minus.
Sir, what is the case in formaldehyde?
Same thing. Whatever be the aldehyde, whatever be the ketone, this is going to be the same thing.
There will
okay,
be
again, there is no OH bond there. What is your question? Yes, go on.
There will be hydrogen in CHO, right?
Hydrogen attached where? To carbon or oxygen?
Carbon.
Then that is how does that going to play any role?
Oh, okay, sir.
Right. Okay. Next. Okay. Explain why orthohydroxybenzaldehyde is a liquid at room temperature, whereas parahydroxybenzaldehyde has a high melting point. Look at this, people. Very good question. They are telling orthohydroxy hydroxy benzaldehyde is there, and we have para hydroxy benzaldehyde. Now they're telling that this is liquid state. Okay, that doesn't matter. And this is having high melting point. Right now, you see, this is going to be in liquid state because you have a lone pair on this oxygen, and this del plus is going to be there. And what is I'm drawing? This dotted line represents what? Exactly, hydrogen bonding. Okay. Now, what you have to say is, in case of ortho, this thing, we are going to have intramolecular hydrogen bonding, which is going to be weak. Whereas in this case, if I can just show you how it is going to happen. In case of para, you can represent it like this. You have a OH and you have a C double bond O and a H. I'll take another molecule. I'll write C double bond O with a H, and we'll write OH. Now you see that there's a lone pair, del plus hydrogen bonding, lone pair, del plus hydrogen bonding. Right now, you see here in this case, I'm going to have intermolecular hydrogen bonding, which is going to be there. That is going to make sure that it is going to have a very, very, very high melting point. Okay. So whenever intermolecular hydrogen bonding is happening, high bonding point, high melting point will be there. Intramolecular hydrogen bonding is always going to be having lesser boiling point and lesser melting points because it is weaker. Okay. That is how you answer this question. Right. Next, moving on. Right. Suggest a suitable oxidizing agent for this conversion. Right. I see, look at this, what is happening. CH3. Whenever I put something in bracket, that means it's a branch. Okay. CH3, CH double bond, C double bond O, CH3 is what I have. And I want to convert it into CH3, CH3 double bond, CH, COOH. Okay, now you have the double bond here, and that double bond is staying. First of all, this is a ketone, right? Ketones forming acid is very, very rare because ketones cannot be oxidized further, right? So we need to use a very strong oxidizing agent. That is true. And that oxidizing agent should not be able to touch this double bond also. Okay, so all you can go for is CrO3 in the presence of H2SO4. That's the best reagent you will be able to use because CrO3 by H2SO4 is not going to affect this double bond. It is just going to oxidize the ketone to acid. Actually, it's a very bad question. Okay, this is a very bad question, right? Because ketone giving that is an acid, like that's really not a good question. But if at all I had an aldehyde here, instead of this, if I had a H and if I asked you this question, you could have actually gone for PCC. What is PCC?
Pyridine
chlorochromate. Pyridinium chlorochromate will just oxidize your aldehydes to acid, and it will not touch your C double bond. See, but this is a weak oxidizing agent. That's the point. That's why I didn't say this here, right? But if this was an aldehyde, the better answer would have been PCC, and this is a very bullshit question. This is a bad question. Okay, don't worry about this. But if this was an aldehyde, you would have gone for PCC, pyridinium chlorochromate. Okay.
Sir,
Right.
PCC converts primary alcohol to aldehyde.
PCC converts primary alcohol to this thing. No, PCC converts your aldehyde only to acid only. And what I'm saying is correct only. Okay.
Sir,
PCC. What?
Can I check only?
Yeah, sure. PCC. Oh, yeah, Kanna. The PCC, what you told was correct. So the answer would have been this only. Whatever be the case, this would have been the better answer. CrO3 bar H2SO4.
So PCC converts alcohol to aldehyde.
Yes, absolutely. That is true. That is true. So PCC cannot be the answer to this question. Okay, whether it is going to be an aldehyde or a ketone, the answer would have been CrO3 by H2SO4, which is basically going to form H2CrO4.
What if we use KMNO4?
KMNO4 will do this. KMNO4 will break this, and how ozonolysis happens? You will break this and put oxygen. That kind of things, if you will happen if you go for KMNO4, but that is not there in the syllabus for you, right? But all you have to understand is KMNO4. If you go, ozonolysis kind of reaction is going to happen. That will oxidize a double bond also, C double bond C also.
Sir, then HNO3.
HNO3 we cannot use because HNO3 for an aldehyde. No, because HNO3 actually in inorganic chemistry, HNO3 can be used as an oxidizing agent, but nowhere in organic chemistry it will be used as an oxidizing agent.
Okay, sir.
Okay, right? Not only in this, nowhere in organic chemistry. Okay, right. Next, moving on. Write the structure and IUPAC names of the crossed aldol condensation products of ethanol and propan. It's propanol. Okay, it's not propanol, propanol. Okay. Now I don't know whether you know the shortcut, right? I'll give you the shortcut. Okay. So how you can easily get the product out for an aldol condensation? You know the mechanism of this slide. I hope you know the mechanism. Even if you don't know the mechanism, we'll be able to get out the products out. How do you write? Okay. Say for example, now they're asking about only cross aldol, but we'll do the self aldol also. Okay, so we will take ethanol, CH3, C double bond O and a H. We'll write like this. And next compound, how you are going to write this is you are going to protrude the alpha hydrogens of this thing towards this oxygen. So you will write H2, CH, C double bond O, H, or you can write it as CHO. Again, I'm repeating. You will protrude oxygen towards one side and 2 of the alpha hydrogen towards the other side, right? And then you are able to easily remove this H2O to form the final product to be CH3, CH double bond CH, CHO. This would have been the self-aldol product. Okay, same way I'll be able to go for propanol also, but instead of this particular hydrogen, I would have had one CH3 also. CH3, CH2, CHO it would have been. Okay, right? So like that, they're asking you about the cross-aldol product. Let us go for it. Okay, so cross-aldol product, one worst cross-aldol product is you can take the CH3's oxygen this way and the propanols, that is CH, no, how do you write propanol? Propanol is CH3, CH2, CHO, right? This is your alpha hydrogen, right? So these 2 hydrogens only will protrude here. So you will put the CH3 down and you will put CHO like this. And then we will remove your water molecule. So what is going to come out? CH3, CH double bond C, CH3, CHO. This is the one of the product. And how do you name this? Obviously, this is 1, 2, 3, 4. So it is going to be 2-methyl. And you have bute. And in second carbon atom, there is an double bond and al. That's it. So 2-methyl bute 2-enal is what is the answer, the name of the product. Right? What is the other one?
Sir, can you show the before slide?
Yeah, sure. This is self-aldol. Right? Remove H2O, minus H2O. This is a shortcut. You'll remember.
Yes, sir. You can proceed.
Right. So now I'll go for the other product. Other product is where you will put the C double bond O of your propanol, that is CH2, CH3, right? And you will put the H2 of your ethanol. Okay, again, you will remove the water molecule like this, and you will go for CH3, CH2, CH2, CHO. We removed, there's a H also, right? We forgot the H. Okay, CH, double bond CH, CHO. Now, how do you name this compound? 1, 2, 3, 4, 5. So it is going to be pent 2N 1 al, or you don't have to put the 1, you can directly write al. No issues at all.
Sir? Sir, in self, there'll be 2 products, right?
Yeah, again, one more self also will be there. That also will do. So that is basically going to be ethanol with ethanol, sorry, propanol with propanol. So you will protrude 1 C double bond O like this, and you will protrude these 2 hydrogens, that is H2, C, CH3, and CHO is going to be there. Again, we'll remove this water molecule to form CH3, CH2, CH double bond C, CH3, CHO, but this self aldol. Again, you can name it if you want. This is going to be 1, 2, 3, 4, 5. Now, in the second carbon atom, we have a methyl group. So it is 2-methyl. And there are 5 carbon atoms. So pent. Second carbon atom having double bond. So 2N-al. That's it. Again, that is going to be the name. Yeah.
So in the conversion, if we need the intermediate step, we need to add water to this.
Exactly. This is your condensation product. If at all I want the aldol to the whatever the product you form, you add water to that.
Fine, sir.
Okay. Right. That's good. Next. Moving on. Give reason for the following. God, I don't know why are they even asking me this kind of questions. Oximes are more acidic than hydroxylamines. Okay. First, how do you form these oximes, people? You go for any kind of C double bond with 2 more bonds, and you make them react with NH2OH. NH2OH is what is called as your hydroxylamine. And how will you remember the product? Again, you'll remove H2O. So you'll form C double bond NOH. Okay, this is what is called as your oxime. Now they are telling oxime is more acidic than your hydroxylamine. And obviously this OH if I compare and this OH if I compare, which OH can easily come out? Again, we'll be able to speak in terms of stability of the conjugate base. If I remove this, there'll be a negative charge on the oxygen. There'll be a negative charge on the oxygen. And you see, this negative charge is actually involving in resonance. Are you able to understand? Let me write this thing for you one more time. So if I look at the oxime, and if I write the O minus, and if I just write NH2O minus, this O minus is going to be there. Okay, fine, nothing is going to happen here. But you see, this negative charge is actually stabilized by resonance, not even inductive effect. Here we can even speak about resonance here. So obviously here the conjugate base is more stable, and you have to show these structures in the examination. And then you can say that this is a more stable conjugate base. So definitely oximes are going to be more acidic when compared to your hydroxylamines. Okay, right? Fine. Next one. Iodoform is obtained by the reaction of acetone with hypoiodide. Hypoiodide is nothing but your NaOI, right? But not with iodine ion. Now that's very simple because hypoiodide is going to be an oxidizing agent. Now at the end of the day, for example, if I take CH3, C double bond O, CH3 with NaOI, I hope you remember how you form NaOI, NaOH plus I2. Is it not? Now, anyways, now the end products are going to be what? CHI3, which is going to be the yellow precipitate, plus now whichever is going to have this particular one, this one is going to form your CHI3. And this part is going to get oxidized. CH3COO minus. Okay. Now what you have to understand is this hypoiodide is an oxidizing agent. Okay, that is why it is able to oxidize this product, whereas I minus alone, if it is there, it has no oxidizing power. Right? So that is the reason why it is not happening. So the answer to this question is that NaOI, that is your hypoiodide, is going to be an oxidizing agent. That is why it is able to give iodoform test, whereas I minus is not an oxidizing agent. They're asking about iodide ion. Okay, right. Next, oxidation of toluene to benzaldehyde with CrO3 is carried out in the presence of acidic anhydride and not in the presence of H2SO4. I think if you use H2SO4, H2SO4 is also going to be an oxidizing agent, quite strong oxidizing agent, which will convert your benzaldehyde into benzoic acid. Is it not? If you want to convert your toluene, that is, what are they telling? Toluene is CH3. Now, if you go for CrO3 in the presence of what? In the presence of acetic anhydride. That is CH3CO twice O. This is what is acetic anhydride. You are going to form CHO here, right? But the same thing, if I use CrO3 in the presence of H2SO4, you are going to form COOH because now this becomes a very strong oxidizing agent, right? Whereas this is going to be a little weaker oxidizing agent, so it will be able to stop with your aldehyde itself.
Sir,
Okay.
CrO3 is a Jones reagent, right?
Yeah, Jones. CrO3 and H2SO4 together is what is
Yes.
Jones.
Yes.
This is not Jones reagent. This is not Jones reagent, whether this is Jones reagent. Okay. Right. Next. What is the function of Rostley salt in the Fehling solution? Rostley salt. What is Rostley salt? Sodium, potassium,
Tartrate.
tartrate. Right. So basically, we are going to have some Cu2 plus in the Fehling solution. And along with that, you will be adding this potassium. We have Fehlings A and Fehlings B. Fehlings A is your aqueous copper sulfate. This is Fehlings A and this is Fehlings B. Right. And obviously, this CuSO4 is going to form from Cu2O or something that is going to give me some red color. Right. What is the use of this? Sodium potassium tartrate. Right. Sodium potassium tartrate is the one which is the oxidizing agent here. Everything here is talking about only oxidizing agents. Okay. Whereas your tolerance reagent, that itself is an oxidizing agent. So only one solution is okay. But this CuSO4 is not an oxidizing agent. So you have to oxidize it, right? So in that case, sodium potassium tartrate is what is going to be the oxidizing agent here. Okay. Right. Moving on. Addition of Grignard reagent to dry ice followed by hydrolysis gives carboxylic acid, while that of organolithium compounds under similar conditions gives ketone. Okay, now look at this. Dry ice is what? CO2, right? Okay. Now CO2 reacts with RMgX, right? Now what is going to happen? This R minus is going to come and attack here, and this O minus leaves. I mean, this double bond breaks. So we are going to form C double bond O with an R and O minus, and obviously the cation is going to be Mgx plus, right? And when you go for hydrolysis, this Mgx will be replaced with H. So if I start from this R, you are going to form R, C double bond O, OH. Okay, right. Now, when I'm going to use organolithium, none of these things are under your syllabus. I don't know why they're asking you all these questions. Okay, organolithium compounds. That is, now when you have
organic metallic compounds.
So we are going to have R minus and Li plus basically. Right? This is what is going to be an organolithium compound. Same thing will happen. Same mechanism would happen, and you are going to form RCOOH. Okay. But if I'm going to use organolithium compounds, what is going to happen is this is going to react with lithium, right? And this is an acid and base, right? I mean, acid and metal is going to react to form RCOO minus O minus Li plus. Now what happens is one more R minus comes, that will attack here, and this is going to leave. O minus Li plus leaves, and you are going to form RCOR. That is what is going to happen, right? So what am I trying to say is that once you form your acid, right, your organolithium compounds containing lithium is going to be there, that is going to react with acid to form the salt, and this salt can be again easily replaced with another R to form the ketone. Whereas here, we don't have magnesium as such. Magnesium X is there, right? That will not be able to capable of doing this. Okay. Just for the sake of asking questions, they have asked something here. But yeah, these are not going to be in the syllabus for you. Anyways, if they ask you, you'll be able to answer it now. Okay, you have to show the mechanism and rewrite it. Okay, every mechanism you have to show. Okay, next. Why is ethyl benzene not prepared by simple alkylation of benzene? Devise a convenient method for the synthesis. Simple alkylation of benzene, we can prepare, right? So benzene is going to be there. If I use C2H5Cl in the presence of AlCl3, I can expect that C2H5 is going to come here. Why this won't happen? Maybe because it is a little bulky. Okay. So if I have to devise a convenient route for this preparation, what will I do? Benzene. If I make this react with okay, this I can do. Let me show it to you. Okay. So benzene is going to be there, right? Now, first what we'll do is we'll go for CH3COCl in the presence of AlCl3. Now, this is your Friedel-Crafts acylation reaction. So we will get C double bond O and CH3. And I want to convert this into CH2CH3. What should I add here? How do you convert aldehyde or ketone to a hydrocarbon? Two reactions are there. What are the reactions? Go on. How do you convert
zinc amalgam.
zinc amalgam bar HCl? What reaction is this? What is the name of the reaction? This is the name reaction, right? Zinc amalgam bar HCl.
Sir, Clemenson.
Clemenson's reduction. This is Clemenson. What is the other one?
Sir, even simple reduction is possible, right?
If you go for simple reduction, you will convert the
Sir,
C double bond to
Wolff-Kishner.
COH. Alcohol only will get formed. Right? You have to specially go for Clemenson reduction. Or what is the other one?
Sir, Wolff-Kishner.
What is the reagent there?
NH2NH.
So if you have C double bond, don't forget about the other two bonds. If you go for NH2NH2, that is, what is it called as NH2NH2?
Hydrazine.
Hydrazine. Absolutely. Right. Hydrazine. Okay, fine. And then if you go for OH minus, you will convert this into CH2. Same thing can be done with the help of your Clemensons. I think Harshita, I think you have to mute it. Okay, right. Same thing if I write zinc amalgam in the presence of HCl, same reaction would happen. Again, the same thing would come here. Okay, this is the better method of doing it. And why we cannot directly do this is because C2H5 is going to be a little bulky. That's the reason why we'll not do this. Okay, right. Next. That's it. We completed. Yeah, we are done. Okay. Any more? Nothing. Right. If you have any more doubts, you can ask me in tomorrow's class from this chapter. Okay. Right. Thank you so much, people. We'll meet again tomorrow with kinetics. Right. Thank you so much.
Thank you, sir.
Thank you, sir.
Thank you.